Okay, so hey everyone, my name's Jack. Sorry, can you hear me? Okay. Okay, so I'll be talking about quantum state tomography via the random purification channel, and this is based on two works, each of them joint with John, Angelos, and Yuan Tang. The first one came out last November. It's called Mixed State Tomography Reduces to, sorry, it should say Pure State Tomography. And the second one, which should come out maybe next week, is called The Kyle-Werner Algorithm is Not Optimal for Spectrum Learning. So this talk is all about quantum state tomography. This is one of the most basic problems in quantum learning theory. Kind of informally, it's this task. Oh. I can put it into slideshow mode, but then it has this automatic progression.
Oh, I think there's like a button, there's a pause button.
I see. Oh, perfect. Thanks. Okay. So formally, quantum state tomography, you're given n copies of some unknown mixed state row in a d-dimensional Hilbert space with maybe some promise that it has rank at most r. And what you're asked to output is some estimate rho hat, which is supposed to be epsilon close in some distance measure d, with sufficiently high probability, maybe like 1 minus delta at least. So for us in this talk, you can think about d as just being infidelity. Towards the end, I'll talk about a different distance measure, but I'll point it out when I transition to this other distance measure. Okay, so the way you do state tomography, like very generally speaking, is you have to decide on some sort of measurement to perform on your states. And in this talk, I'm going to, in particular, distinguish like two main classes of measurements. So these are unentangled and entangled measurements, respectively. With unentangled measurements, these are measurements where you only measure one copy at a time. So the picture is you have all of your states lined up. You measure the first one and you get some outcome. And then you measure the second one and you get a new outcome, and so on. And then once you've measured all of your states, you piece together all of the bits of information and you use that to produce your estimate. With entangled measurements, on the other hand, this is like the true like power of quantum mechanics, or like the most general type of measurement you can perform. The picture here is you have all of your copies, and then you perform one giant measurement on all of them simultaneously. And now you only have one measurement outcome, but it contains all the information you need to generate your estimate. Okay. So unentangled measurements are desirable. Like we'd like them if we can get them, algorithms which use them rather, just because they might be more practical to implement in the lab. But for kind of like considering like the information theoretic limits of our problems, we're not going to restrict ourselves to unentangled measurements necessarily. We'll allow ourselves to use fully entangled measurements. Okay, let me also say some things we care about in particular. So what we're primarily interested in is the sample complexity of our algorithms. This is how many samples an algorithm needs to use in order to successfully learn a good estimate for rho. And we're interested in how that sample complexity scales with the parameters, like the rank r, the dimension d, and like your error epsilon and failure probability delta. And we're interested specifically in algorithms which like minimize the sample complexity across all algorithms. It's like, so these are the algorithms that use the fewest number of copies. And we'll call those sample optimal algorithms. And then also, when we can get them, we're also interested in computationally efficient algorithms. So again, we won't necessarily restrict ourselves to only focusing on such algorithms, but when we can get them, it's nice to have algorithms that we can actually implement with polynomial resources. Okay. So let me sketch for you the where sample optimal tomography kind of was before the random purification channel. So I'll compare and contrast kind of like two types of tomography. We'll consider like the pure state tomography, which is the special case where your input is pure. And we'll compare that to the more general problem of tomography where your input can be mixed and have large rank. So first we can ask about like what are the sample complexities of these problems? And for pure state tomography, the answer, like the sample complexity is like, it's like well established. So we have matching upper and lower bounds. They've essentially been known since the 90s. And that sample complexity is d plus log 1 over delta, all of that divided by epsilon. For mixed state tomography, the answer is, well, the sample complexity is not quite as settled. So we have matching upper and lower bounds up to log factors of rd plus log 1 over delta divided by epsilon. And these results are much harder to obtain, and they started appearing in like the mid-2010s. So the tilde, maybe I can clarify this a little bit. If you don't care about delta at all, like if you only want your algorithms to succeed with like constant probability, then we actually have matching upper and lower bounds of rd over epsilon. But if you care about delta scaling, then the upper bounds, the best we have is like a tilde upper bound. So we don't truly know like the scaling with delta. Okay, so we can also ask maybe for some nice properties we might want our algorithms to have. So we can ask, are there sample optimal algorithms which can be efficiently implemented? And for pure state tomography, the answer is yes. But for mixed state tomography, the answer is like we don't have one yet, at least. We don't know they don't exist, but we don't have one. We can also ask, can we get away with doing sample optimal tomography while only using this like simpler kind of measurement, the unentangled measurement? For pure state tomography, again, the answer is yes. And for mixed state tomography, the answer is actually that like provably you cannot do this. So you must use entangled measurements in order to do sample optimal mixed state tomography. And finally, we can ask maybe a more subjective question, but like, are these algorithms simple? So are they like easy to think about and or to use and practice to compute things? And I think it's fair to say that for pure state tomography, the answer is yes. These things are essentially like symmetric subspace calculations, or that's like the kind of analysis that you're doing when you work with these pure state algorithms. And for mixed state tomography, I think it's fair to say that the answer is no. So these things are much more complex. They're representation theoretic, and they're, I would say, harder to think about and much more difficult to compute with, and just generally more complicated. And so it seems, yeah, question. Yeah. That's right, that's right. Like you can always do like Pauli tomography, for example. Yeah. Okay, so it seems from this picture that at least for sample optimal tomography, pure and mixed state tomography seem very different. Like pure state tomography is very nice. We have like pretty much everything we want from it. And mixed state tomography, we don't know everything and we don't have everything we want, and it just seems much more complicated. But actually, I'm here to tell you that this is not the case. That in fact, mixed state tomography reduces to pure state tomography, and we can use all these nice simple pure state algorithms to do mixed state tomography. Okay, so the goals for my talk will be to describe this reduction and give you like a simple framework for doing mixed state tomography from pure state tomography. And the main tool, of course, given the workshop, is the random purification channel. And then I'll show you how we can use this framework to recover or improve upon and go beyond essentially like everything we've known so far with mixed state learning. And hopefully I've convinced you by the end that like the random purification channel is like the tool for doing mixed state tomography. Okay, so I'll start by just reviewing some relevant aspects of the random purification channel. John just talked about this, but I'll just remind you. It's possible to efficiently construct a random purification of a mixed state. And specifically, we have this theorem that there's this channel, which I'll denote purify, that takes in n copies of a rank R mixed state. And what it outputs is a uniform mixture over all possible purifications of n copies of that purification. So you can view this channel as you sample a random purification, and then I give it to you n times. And moreover, this channel can be implemented efficiently. I just want to particularly emphasize two features. The purifications live in a larger Hilbert space, of course. Here, if you're purifying rank R states, they live in a d times r dimensional Hilbert space. And the other thing I want to emphasize is that the purifications are consistent across the n copies. So I'm not giving you n independently drawn random purifications. The purifications are all the same. And this will be really important for our tomography. Okay. All right, so I'll kind of sketch now how you might do this reduction, and then I'll come back and show you exactly how it's done. So the idea is, mixed state tomography is super complicated, and it'd be great if you could just use the pure state algorithms and do something like the following. So you somehow convert your mixed states row to copies of some fixed purification, ket row. Now that you have the fixed purification, well, you just choose your favorite algorithm A for doing pure state tomography. And then you run that pure state tomography algorithm in the larger Hilbert space. And you learn an estimate for the purification. And finally, what you do is you just trace out the auxiliary registers. And this will give us mixed state tomography, because if the pure state that you learn is close to the true purification, then upon tracing out, the mixed states will be close as well. Now, there's one problem with the exact outline I just gave, and it's that, as John mentioned, preparing fixed purifications is hard. But actually, it doesn't really matter what purification you produce. You can produce any purification, and because we're tracing out the auxiliary information, it doesn't matter which one you prepare. And in particular, you can prepare a random purification. Okay? And since we can do this algorithmically, this gives us the framework. So here is the reduction. You give me a pure state algorithm A, and I'll give you back mix of A, which is a mixed state algorithm. So it takes in n copies of a mixed state row. You use the random purification channel to produce a random purification. You use your pure state algorithm to learn that purification in the larger Hilbert space. And then you finally just trace out the auxiliary registers to get your estimate of the mixed state. Okay, so now the question is, which algorithms should we actually be putting into this reduction to get, the things we want? So let me just remind you of some goals of ours. One goal would be to get an algorithm with optimal sample complexity in like all parameters, including delta. Another goal might be to get an algorithm with an efficient implementation. A third goal might be to, I'm going to claim that like this is like a really nice way to do tomography. So I should kind of at least show you that we can get everything we knew how to do before. So we'd like to recover old applications. And then, hopefully also some new applications, right? This is supposed to be like a simple framework for doing tomography. So we should have like some more power in analyzing our estimator, and hopefully use that to get some new results as well. Okay, so for the first two goals, I'm going to use a certain algorithm, the unentangled algorithm due to Gute, Kahn, Kung, and Trop. I'll talk more about this in a second. But the idea here is that this algorithm is both sample optimal and efficiently implementable. And the mixed state version, mix of A, is going to inherit these properties from that algorithm. But it's actually not going to be powerful enough to do everything we want. So for the remaining goals, I'm going to use a different algorithm due to Hayashi, which uses entangled measurements. It's a stronger algorithm, and we'll be able to use this to do more. That's true. So whereas we could use Hayashi also to do the optimal sample complexity, as John just said, it's not known to be efficient. So we would miss this like second goal if we just used Hayashi's algorithm. Okay, so let's start with this first algorithm and use it to get sample optimal and efficient mixed state tomography. So let me tell you about this pure state algorithm, the GKKT algorithm. It performs a measurement on each copy individually. Specifically, it does the so-called uniform POVM. If you'd like, you can think about this as sampling a random basis for each copy and then measuring in that basis. But if you're interested in the POVM element, what it does is it has one POVM element for each possible pure state output, and that POVM element is just projection onto that pure state. Upon measuring like an outcome labeled by a pure state U, thereby getting like this like U hat, and then like the I means this is from like the ith measurement on the ith copy. What the GKKT algorithm does is it essentially returns like this pure state, but up to a linear transformation, which represents a de-biased version of the pure state. Okay, so you don't need to worry too much about this expression. Just think of this as a de-biased version of returning the pure state. And the reason we're doing this de-biasing is because these POVM elements, they're weighted towards returning the right state, but they're not weighted particularly strongly. And so individual estimates might be kind of crummy, but what we're going to do is we're going to average together many, many of these. And because it's unbiased, we're going to converge to the right mixed state. And then finally, at the end, you can round to like the closest pure state if you really want to output a pure state in particular. Now, the GKKT algorithm has the following guarantee. So you feed it n copies of a pure state psi, and what the algorithm does is it outputs an estimate psi hat such that psi and psi hat have good fidelity with high success probability as soon as you use like n that scales with d plus log 1 over delta divided by epsilon. And this is the sample complexity of pure state tomography. We have matching lower bounds. So this is like the best that a pure state tomography algorithm can do in terms of sample complexity. And finally, it can be implemented efficiently. Okay, so what happens if we put this into our mix framework? Well, you feed into your algorithm n copies of a mixed state row. It purifies to the larger Hilbert space. And then you're going to run GKKT on this larger Hilbert space. And provided you take n to be like the sample complexity of learning pure states in this larger Hilbert space, which now has dimension RD, then what you're going to get is a good pure state estimate in the larger Hilbert space, which has, it has good fidelity, and you have good success probability as well. And then finally, you trace out the auxiliary register, and because fidelity is monotonic under this tracing out map and only increases the fidelity, you know for sure that your mixed state estimate is going to have high fidelity as well. Okay. And so this gives us the following result. Mix of the GKKT algorithm returns a mixed state estimate with high fidelity and high success probability when you use RD plus log 1 over delta divided by epsilon samples. And moreover, because the random purification channel can be implemented efficiently, and because the GKKT algorithm can be implemented efficiently as well, their concatenation can. And so we can run this mixed state tomography algorithm efficiently as well. Okay, so just to compare, we have this lower bound, which matches the sample complexity. And so we can go back to our goals, and we can see that the first one was to get an algorithm with optimal sample complexity in all parameters. And this algorithm does that. And it's also efficient because of this concatenation that I just described. And I think a case can also be made that it's pretty simple. So the analysis for the sample complexity that I just described is pretty much like the entire analysis. And it goes beyond more complicated representation theoretic estimators of the past, which involved quite lengthy analyses and didn't get the right scaling, and we didn't have efficient implementations for them. So this algorithm kind of has a very simple description and also a simple analysis. So I'd say it's kind of simple. And finally, just before moving on from this algorithm, I think there's something interesting to remark. So I told you before that mixed state tomography algorithms, must use entangled measurements somewhere in order to do sample optimal mixed state tomography. But in this algorithm, once we've prepared the purifications, we can get away with just using unentangled measurements. And so it kind of clarifies, perhaps where the entanglement is actually necessary. And in this algorithm, it's necessary for producing the consistent purifications. It's actually in the random purification part of the algorithm. Okay, so now I'm going to shift gears, and I'm going to talk about how we can use a different pure state algorithm to not only recover some previous applications, but also go a bit beyond. All right, so I'll begin by just describing Hayashi's algorithm, which is the second pure state algorithm. Hayashi's algorithm is, as I mentioned before, it's a sample optimal tomography algorithm for pure states. But actually, it's in a certain information theoretic sense, it's also the best one. So it's stronger than the one we considered before. It does use entangled measurements, and we don't currently know how to implement it efficiently, but we'll be able to use it to get better sample complexities. Okay, so what this algorithm does is it measures with a POVM element on n copies simultaneously. That kind of looks like an n copy generalization of the GKKT algorithm. And so its POVM elements are labeled again by pure states, and the POVM element is projection onto n copies of that pure state. And upon measuring some pure state, you get some outcome U hat. And what Hayashi's algorithm does is it just outputs this pure state directly. Here, the POVM elements are much more strongly weighted towards returning states with good fidelity with your true state, which is necessary because you only get to do this measurement once across all of your copies. So in practice, actually, we're going to be considering a slight modification to Hayashi's algorithm called the GPS algorithm after its finders Greer, Pishayan, and Schaefer. but you should just think of this as an unbiased version of Hayashi's algorithm. You do the same measurement, and then you do the same kind of linear transformation, which you don't have to worry about, but it's kind of a simple transformation, and it's just like an unbiased estimator for the true pure state. So what can this get us? Well, this algorithm is pretty strong, and it can be used to recover like pretty much every application in mixed state tomography that we knew about before. So in particular, I'll just talk just briefly about some 3 applications that in previous work, John Angelos and I used one of these representation theoretic mixed state estimators, which we called the debias-Cowles algorithm, to obtain like improved or optimal algorithms for these problems. So these 3 problems were, well, the first one was K-entangled tomography. This is tomography, but you're restricted to only measuring K copies at once. And so what this problem studies is kind of like the trade-off with sample complexity and the strength of your measurements. The second problem was classical shadows, which is a variant of shadow tomography. In this problem, you're given observables, and what you're tasked to do is produce estimates for the expectation values of the observables in the unknown state that you're given. So you don't have to learn the full state, you just have to learn these expectation values. And the final problem is in this field of quantum metrology, and I won't say too much about this problem in particular, but kind of the flavor is that you're given copies of a parametrized mixed state rho theta, and what you have to do is you don't have to learn the state, but you do have to learn the parameters associated to your input state. And so for these 3 problems, it's very convenient to have an unbiased estimator. And in our previous work, we spent a lot of effort trying to unbias or debias one of the existing representation theoretic estimators. And for these applications in particular, like once you have an unbiased estimator, kind of your analysis relies on just like the quality of that unbiased estimator, which involves analyzing its second moment. So in this work, we really had to find, to compute like the second moment of this representation theoretic estimator, which was a bit hard, but we did it, and we got some improved results or optimal results for these problems. But in like our new work, like this framework, because the GPS algorithm is itself unbiased, the mixed state version, mix of GPS, will actually inherit this result. And so we kind of get unbiased very cleanly. And in fact, its second moment is actually also not terribly complicated to compute. It's a symmetric subspace calculation. And what we can show, kind of surprisingly, is that mix of GPS actually matches this second moment. And since our applications to these 3 problems only depended on those first 2 moments, we actually get all of those applications, we recover them with like much less work. Okay, so despite me talking up how much simpler mix of GPS is relative to debias-Cowles, I still think debias-Cowles is a very cool algorithm, and Angelos will be talking about it on Friday. And you should check out that talk. He'll go into more depth about all of these problems and the particular algorithms that we use like once we have an unbiased estimator. Okay. So I've talked about some existing applications. Let me talk about some new ones. So I'll talk about 2 kind of briefly, and then I'll go into more depth on a third one. So the first kind of brief application I'll talk about is to this problem of principal component analysis, or PCA. And in this problem, you want to do tomography, but instead of learning the full state, you just want to output like the best rank K approximation in some distance measure. Now, this problem was previously considered in work of O'Donnell and Wright, And they used a representation theoretic estimator to show that you could do trace distance PCA with sample complexity KD over epsilon squared. We can recover this result with our new algorithm mix of GPS, but actually we can go a bit beyond it. We can do principal component analysis also in Burr's distance, which is generally thought of as like a harder distance measure. It's essentially like learning in fidelity with the same sample complexity. We also considered the problem of like learning in more stringent distance measures. So in particular, there's this Burr's chi-squared divergence. This is a harder distance measure to learn in than trace distance or fidelity. And if you can learn in chi-squared divergence, then you automatically learn in trace distance or fidelity. And there we show a certain sample complexity, square root RD cubed over epsilon, which removes the tilde from the best known previous algorithm due to Flamey and O'Donnell. Okay, so the main application I want to focus on is to spectrum learning. So what is spectrum learning? Informally, it's this problem of you get copies of an unknown state and you want to learn the eigenvalues of that state. And formally, you have input n copies of rho with sorted spectrum alpha, and you're asked to output some estimate alpha hat, which is supposed to be close in total variation distance with, say, high constant probability. So that's the problem. There's a classic algorithm for this task. It's called the Kyle-Werner algorithm. It's from 2001. It's this really clean representation theoretic measurement. It's often like also like the first step that you do in these more complicated mixed state algorithms, but it's like a very clean first step. And I won't really describe it, but I'll tell you its sample complexity. It uses d squared over epsilon squared copies of rho. It must use this much, and you can get away with using this much. And what's interesting about the sample complexity is that it's already as many copies needed to learn the state in trace distance. And if you learn the state in trace distance, you've learned not only the spectrum well, but also the eigenvectors well. So it seems like you're doing much more work, or it's like you're using as many samples as could be used to do much more work, but so it's like you're not really, what do I want to say? Sorry, you're using as many copies as could be used to learn so much more. And so it seems like, maybe you can really save on this sample complexity, perhaps. So the natural question is, we only want to learn the spectrum. Can we do better by using fewer samples and not learning the eigenvectors? Okay, so let me give you some maybe competing intuition for and against. So the for intuition is kind of what I just said. It's like you only have to learn the eigenvalues, not the eigenvectors. And the eigenvalues, there are only d of them, so they're order d parameters. Whereas for the eigenvectors, you have d eigenvectors to learn. Each of them has d coordinates. And if you're learning the full state, you're also learning the eigenvalues. But you have like order d squared parameters to learn if you're learning the full state. So, maybe you should be able to do much better, right? Because you're learning much less. Maybe competing with this, you can kind of think of like a quantum state. It's like a distribution over the eigenvectors, and the eigenvalues tell you like the probability of sampling that eigenvector, right? So you can kind of think of what you're trying to do is you're trying to learn the frequencies of the eigenvector in the state. And so you might think like, okay, I just want to measure these frequencies, but with less than d squared copies, you can't even know the eigenvectors themselves. And so maybe there's this feeling of, well, how could I learn the right frequencies that these eigenvectors appear in our state? And maybe also more concretely, there's actually some numerical evidence that suggests that you can't improve on d squared by like a polynomial factor. So like here, gamma is any constant. Okay, but maybe back in the positive direction, maybe we can actually improve on it a little, because there turn out to be analogs of this problem where it's known to be the case that you can improve by like polylog factors. So let me describe these quickly. So the first analog is the classical special case. This is the problem of you're given a probability distribution, and what you want to learn is just the sorted distribution. So you don't have to learn like which probability goes with which event, but you just need to learn the probabilities. And here, the number of copies required, or samples, sorry, in the classical case, the number of samples required to learn the distribution is d over epsilon squared. And it's known what like the sample complexity of learning the sorted distribution is. It falls into two cases depending on like how large epsilon is. So like when epsilon is very small, if you're trying to learn this very accurately, it turns out you can't do better. But when epsilon is kind of large, so here gamma is again any constant, you can actually improve on this by one log factor in d. And there's also an analog that's quantum, but is known in like the special case where all of your learning is done with unentangled measurements. This is work due to John, Angelos, Ewan, and Nora Tan. Well, they're comparing against learning the state, which with unentangled measurements uses d cubed over epsilon squared copies. And what they showed in their paper is that you can learn the sorted spectrum in this sample complexity, which I'm going to rewrite by factoring out a d cubed over epsilon squared. So what we would like is for this term in the inner parentheses to show that it can be like much less than 1, right? And in particular, this is the case if epsilon is sufficiently large. So it has to be like larger than 1 over essentially like log d. So when epsilon is this large, you improve on just doing tomography. And so what we show in our upcoming work is that this is also true for entangled quantum state tomography and spectrum learning with entangled measurements. And we give the first improvement over the Kyle-Werner algorithm for some parameters. Kind of what we show is that with a new guarantee on tomography that holds for this GPS algorithm, a mix of GPS, we're able to show that there exists an algorithm for spectrum learning using this sample complexity, d squared over epsilon to the 4 times log d squared divided by log d squared. And we can make the same kind of comparison with Kyle-Werner or full state tomography. So that was d squared over epsilon squared. And if we do the same kind of trick where we factor out d squared over epsilon squared, we see that like we can make this term here much, much smaller than 1 by taking epsilon to be like essentially larger than 1 over log d. So for some parameter regimes, we are improving on Kyle-Werner, and this is the first time that there's ever been an improvement to Kyle-Werner. Okay, so let me just talk to you about this new guarantee which makes this algorithm possible. It's really key to our analysis, and it's also the main tool that we use for proving like our PCA and chi-square divergence improvements as well. So what the guarantee says is that if you're using mix of GPS to do your mixed state estimation, then with high constant probability, 99%, for all states W simultaneously, we have the following bound. So what this bound is saying is that it's like you look at how much rho hat deviates from rho in like the W direction, and we give a bound which depends on how big rho is in that direction. And in particular, when this when rho is quite large in this direction, we have a bound that looks like this. So it has, it's improving as rho becomes smaller in this direction, until eventually you hit some floor where we can't make any guarantee besides maybe some d over n size. Okay, so why is this useful for spectrum learning? I'll just sketch the reasoning, like some intuition. Well, it's because the principal difficulty of spectrum learning is separating your, it's like bucketing, which is kind of deciding which eigenvalues are big and which eigenvalues are small. And the reason we want to do this is because our algorithms kind of learn the big eigenvalues and the small eigenvalues separately. And you need to learn the small eigenvalues separately from any of the big ones. Otherwise, like the large eigenvalue ends up contaminating how well you can do to learn the small eigenvalues. And the reason why this bound is useful then is because it allows us to get better control in directions where rho is smaller. So it allows us to say, okay, these directions, rho is quite small, and we can guarantee that like a big eigenvalue is not ending up in the directions we think should be small. So that's kind of like the reason why this bound becomes useful. Okay, let me tell you some more about this guarantee. We can compare to the classical case. In the classical case, what you're doing when you estimate a probability distribution is like forming a histogram from your samples and using this to, like you normalize that histogram and that becomes your estimate. And so your p hat is like it's like a binomial random variable, right? And the variance of this random variable shrinks, right, as the probability becomes small, right? So what we see in the classical setting is that p hat, fluctuates less on events I where the probability is small. And in fact, you can do maybe some more work, you can do some Chernoff bounds, and if you also union bound over all d events simultaneously, then you can show a result which looks very similar to like the quantum bound that we have. So here the main differences are like you're only looking in, or like in the quantum case, you could look in any direction, but in the classical case, you can only look in like directions defined by the events, right? So instead of having like rho hat minus rho in the w direction, you just have rho hat I minus, p hat I minus pi. And the other main difference is instead of having like a d, we have a log d. But you can think of this as coming from like the union bound. So in the classical case, you union bound over d objects and you get a log d appearing. But in the quantum case, you kind of have to union bound over, you can think of it as like a net of quantum states, which contains like e to the d many states. And so instead of having a log d, you have like a log of e to the d, and so you end up with d's here instead of log d's. Okay. So in this sense, our bound is quite analogous to this classical one. And what it's showing is that rho hat is fluctuating less in these directions where rho is small. Okay, and I'll also mention that this bound improves in a certain sense, which I'll describe over like this L infinity bound proven by Gute, Kahn, Kung, and Trop. So the bound that they showed is that with high probability, with high constant probability, rho hat and rho differ, their difference has infinity norm bound of like square root d over n. And now it turns out you can't improve on this bound, its scaling, like for all states, because that would actually imply better tomography algorithms. But what you can do is you can improve on it in certain directions. And so that's what our bound is doing. So for example, you would obtain this affinity norm bound from our bound by maybe taking the supremum over all w. You can upper bound this term here by 1. In which case our bound reduces to their bound. Okay, but for most directions, rho is not going to have overlap with W1, And so we get something stronger for certain directions. Okay, maybe I can also give you some further intuition, like a heuristic way to understand this bound. What you can do is you can actually compute the left-hand side, the variance of this term here. This can be done using some techniques from our first paper. We gave an expression for the second moment, and you can just use this to compute the variance. And what you get is this variance here, which looks essentially the same as what's under the square root, except without this d. Okay. And now, if you imagine that this fluctuation were distributed as like a Gaussian with, say, standard deviation sigma, then we would have a bound on the probability that this fluctuation is more than like square root t times sigma. And that bound would be, it would be like exponential in minus t. Okay, so that would hold for any fixed w, but we want some bound which holds for all w. And so we want to take a union bound over like a net of states, which involves union bounding over e to the d many states. So we want to take this t to be at least d to get a result that holds with high constant probability. And if you plug in d here, then this bound on the right becomes exactly this bound at the top. Okay. Now, this is only a heuristic way. It turns out that these fluctuations are not actually Gaussian. They're actually sub-gamma. And you can't quite do the net argument like this because you would be drowning out the information about the directions when you take like a supremum over the net. But kind of like morally, this is what's going on. And I can actually kind of sketch how the proof goes. The exact steps are not too important. I just want to state them just to make a point at the end. Kind of the way our proof goes is by showing a result for pure state tomography with like the GPS algorithm, showing that observables have sub-gamma concentration. And then using our mix framework to have mix of GPS kind of inherit this. And that step there is actually quite simple. And finally, the bound we end up applying this to a particular observable. But the step I really want to emphasize is this first to second step. Like the power of this mix of GPS here is coming from like an inherited statement from the pure state case. And so most of the work ends up going to proving a result in like the simplest case, the pure state case, and we don't have to directly go to the mixed state case. We have this nice inheritance. Okay, so I'll start to wrap up now. So to start concluding, let's just revisit this table that we had at the beginning of the talk. And let's look down the mixed state column where we had a lot of red or things that we didn't have or things that we would like to have. So we didn't know what the true sample complexity was for mixed state tomography, in particular for delta. But now we do. And we didn't have an efficient implementation for mixed state tomography, but again, putting the GKKT algorithm into our framework does give us one. When it comes to whether we can use unentangled measurements, we can't change this to yes because it was proven that you must use entanglement. But we can kind of put an asterisk here. Maybe conceptually, it kind of refines our understanding of where this entanglement is actually useful. Since we can use the random purification channel followed by an unentangled algorithm, where like the learning is done in an unentangled way, suggests that like the entanglement is necessary perhaps for producing the consistent purification. And finally, the algorithms that we get are much simpler. So you avoid a lot of this representation theory and reduce the algorithms to symmetric subspace calculations. And finally, we're also able to recover the existing applications of our previous estimators, and we can go beyond and get new applications helped by like the simplicity of our estimators, which helps us to analyze further. Okay, so hopefully I've convinced you that the random purification channel is a powerful tool for mixed state tomography. Let me conclude by mentioning some related talks this week and a couple open problems, which I think are cool. So there are several other talks on tomography this week. In this workshop, we have talks tomorrow on channel tomography and also tomography of physical systems on Wednesday. These two talks also use random purification ideas. And then Angelos is also presenting on our previous work on the debiased Kyle's algorithm, and he'll go into more depth about not only the applications, but the algorithm itself, which, okay, may be representation theoretic, but I think what it's doing is still pretty cool, and I hope you come to that too. And finally, I'll conclude with some open problems. One of them is just what is the true sample complexity of spectrum learning? So we've given an algorithm which improves over Kyle-Werner. So we know it's not d squared over epsilon squared, but what is the true sample complexity? We conjecture it should look like this by analog with the classical case. So it should have the scaling of full state tomography, the d squared over epsilon squared, but maybe improved by a couple log factors provided epsilon is sufficiently large, but we don't know. And finally, another open problem is for tomography tasks, is the random purification channel essentially all you need? Or are there genuine tasks where it's much better to just do something else? So there's this recent result that one of these representation theoretic algorithms, Kyle's algorithm, is actually asymptotically optimal in a certain information theoretic sense. And so I think it's an interesting question to ask, is there a natural problem where you have a sample complexity separation between Kyle's algorithm and say mix of GPS or something like this? All right, so I'll stop here. Thank you.
Your new guarantee for tomography looked like something one could also get from a relative error bound in Launer order. Have you thought about something like this? Is it something that
Oh, sorry, I missed it. A relative
in PSD order, say rho hat minus rho is less than something as a matrix in the matrix order?
I don't think we have a. Oh, sorry. I don't think we have a PSD statement. Yeah.
Anyway, I think it's an interesting question. Do you know if there is any kind of guarantee on the relative error in Launer order?
I'm not sure. Yeah.
Okay.
Yeah, it's interesting.
Thanks.
Just on the unentangled measurements, does one of these papers do the algorithm with R squared D dependence?
Yeah, the GKKT algorithm uses R squared D dependence, yeah. I guess I only talked about it in terms of using it as a pure state estimator, where R is 1. But yeah, it's also a mixed state estimator for all R.
Yeah, I have a simple question. So for the other application of tomography rank R state you mentioned, is it true you only need guarantee that the state has rank no larger than R, but not necessarily exactly?
That's true. So the algorithms all extend, if you were rank R minus 1, you could also use the rank R algorithm.